The second talk will be given by Jason Picardo on Lagrangian irreversibility and intermittent dissipation in turbulence. Jason, are you with us?
Yes, hi, Luca.
Okay, hi, Jason. So you have a 20 minutes talk. If you stop 2-3 minutes before, we can also leave room for questions. Please go ahead.
Sure, thanks, Luca. I'll just get my slides up. Sorry, yes, I meant to turn off my video because my connection is not that great. Okay, I hope you can see my slides. Okay, so yes, so it's a pleasure to be here today. Grateful to the organizers for setting up this meeting and giving me a chance to talk about my work. So in this talk, I'll focus on Lagrangian irreversibility of fluid particles as they navigate an intermittent dissipation field, which is characteristic of turbulent flows. So let's get started with the basic question that motivated our work. So as we know, turbulent flows are irreversible, and this follows almost trivially from the fact that they dissipate a mean amount of energy per unit volume. But if we zoom in and look at it more closely, as we all know, the dissipation field tends to concentrate into regions of intense dissipation, which, at least at the modest Reynolds numbers I have here in this cube, take the form of sheets. So this is for Taylor Reynolds about 100 to 200. And what I've done here is just shown a visualization of regions of constant energy dissipation, about 4 times and 6 times the mean. And so this is typical, and of course, they become even more extreme at larger Reynolds numbers, as we've seen in the many excellent talks of the first 2 days. Okay, so the question we are interested in is, if you imagine a fluid particle or a tracer navigating through this flow and encountering one of these intense dissipation sheets, how would this fluid particle kind of experience this intense zone? And more specifically, if we think about the kinetic energy fluctuations of this particle, then that question relates to Lagrangian irreversibility. And this is an issue that was addressed in the hallmark paper by Zhu, Alain Poumire, Falkovich, Borenschatz, and others in this PNAS paper in 2014, which I'll refer to as the flight crash paper. And so basically what they found here and showed with both experiments and simulations is that the kinetic energy of a tracer particle grows gradually and then is lost in sudden crashes. Of course, in the long-time average, it stays the same if the flow is forced in a statistically stationary manner. But in time, you see that there are gradual energy gains and sudden losses. So another way to kind of formulate the question is, do these fluid particles experience their crashes of kinetic energy when they encounter regions of intense Eulerian dissipation? Now, this kind of correlation between the two is sort of appealing, even at a visual level. You can imagine, these particles moving through the flow, gaining energy slowly in the mild ocean, if you like, and then crashing when they encounter one of these intense sheets. Another reason, that kind of makes this a little plausible is the very nice result by Alain Poumire and co-workers, PRL 2016, where they showed that the signature of flight crash, which is kind of the negatively skewed distribution of power of the tracers. So they showed that this negative skewness can be related to the mean vortex stretching, which, as we know, is positive and leads to, depending on the sign, but there is net stretching of vorticity in turbulent flows, which is central to the cascade of energy and the growth of intense vorticity. So that mean can be tied directly to this to the Lagrangian irreversibility signature. So, of course, this is a result in the mean on the average, but it's still tempting from this to kind of think of it locally and, imagine that these things could be crashing in regions of intense small-scale activity. So this is the question that we will probe, and I would say beforehand that what we find is contrary to this view and was rather surprising to us initially. Okay, so this work is out in PRF, and it was done with Akshay Bhatnagar, who is at Nordita in Stockholm, and Shamridhi Shankare at ICTS in Bangalore, with whom I did a postdoc. And that was a few years back. Now I'm at IIT Bombay in Bombay, India. Okay, so let's first briefly look at the tools and kind of simulation strategy we'll be using to address the question. So of course we do standard pseudospectral DNS of Navier-Stokes in a periodic cube, and we have a kind of stochastic in-time forcing that maintains a fixed amount of energy being pumped in at the large scales, and so we have a fixed time averaged volume average dissipation. The Taylor Reynolds is pretty modest at 111. So into this flow, I release a bunch of tracer particles and track their motion in the standard way, and also calculate the energy of these tracer particles. So if I have the energy, the kinetic energy of these tracer particles, then I can calculate the time derivative of that energy following the particle, which gives me the Lagrangian power. So the signature of flight crash events is related to the kinetic energy fluctuations or the distribution, the PDF of the power. So here's a figure from the flight crash paper of 2014. And what's shown here is the distribution, the PDF of the power scaled with the mean dissipation epsilon. And the dashed lines show you the negative tails of the PDF reflected onto the positive right-hand side. So you see that the negative tails are higher systematically than the positive tails, which indicates a negative skewness of the power. And this implies that you have sudden crashes of the kinetic energy. And so this negative skewness of the power is really the signature of Lagrangian irreversibility and specifically of what's called flight crashes in this paper. So we'll be using this basically as a basic diagnostic, and trying to relate this to this power PDF fluctuations to the particle traversing intense or mild regions of dissipation. Okay, so that's on the one hand, we have the standard Navier-Stokes simulations. Now, as a complement to that, we thought it would be very nice to investigate the motion of tracer particles in a flow field that has the properties of turbulence, especially for us, irreversibility, its chaotic nature, apparent stochasticity, but which lacks extreme events of dissipation. And one such system that's particularly nice for our study is the decimated Navier-Stokes equations. Now, this system yields a turbulent field that's non-intermittent in a sense that I'll show you in a second. And while it dissipates the same amount of energy in the mean, it does so in a more kind of smooth way without extreme events. Now, this system was introduced and studied by Shamridhi, Luca, and their co-workers in these PRL papers, and then in several follow-up studies where these properties of it being non-intermittent and lacking extreme events were explored in greater detail. So here we shall adopt this system as a kind of flow field into which we put in our particles and study whether the Lagrangian irreversibility of the particles are at all affected by the lack of extreme dissipation structures. So just to show you what I mean by loss of extreme events, the cube on the left is the one I showed you earlier. It shows you the extreme dissipation sheets in standard Navier-Stokes turbulence. And on the right, you see a result from the decimated Navier-Stokes simulations. The total amount of energy in the entire volume being dissipated is the same. But you see it's done so in a much more regular way, where the number of extreme blue sheets, which correspond to about 6 times the mean dissipation, are lost in the decimated flow. I would like to note also that this loss of small-scale extreme structures was noted and shown before by Lenoth and Luca and others in 2016. Here, this is a plot of their vorticity field where you see that these intense tubes are also lost. Okay, so without spending too much time, the basic idea in the decimated Navier-Stokes is to apply a generalized Galickian projection operator P, which basically says that if you decompose the Navier-Stokes in Fourier space, and then you knock off a subset of Fourier modes. So this gamma k, if you set to 0, essentially eliminates a corresponding Fourier mode with wave vector k. And so I can then choose this gamma k in different ways. So what we do is set it randomly at the beginning of the simulation and then keep it fixed. And so the probability of knocking off a mode of wave number k can be done in different ways. One way is to just take the probability to scale as a power law with the magnitude of the wave number. This gives us the so-called fractal decimation, where capital D is the fractal dimension of the surviving set of Fourier modes in Fourier space. Another simple alternative is to just keep a constant probability of knocking off a Fourier mode regardless of the wave number magnitude. And that's measured by alpha, and it gives us homogeneous decimation. So the main take home here of this kind of formulation is that if you have the capital D going to 3 in the case of fractal decimation, or alpha going to 0 in case of homogeneous decimation, you recover the 3D Navier-Stokes in all its entirety. And if you take other values for this, you can progressively decimate the equations. So the actual system I'm evolving looks like this, where the projection operator acts on the nonlinear terms, and you can evolve it forward in time. Okay, so just as a final kind of demonstration of the loss of extreme events. So you have here what I showed you before. If you measure the power PDF of the local dissipation, normalized by its mean value, the black lines in both the plots correspond to the Navier-Stokes case. The left plot shows you the effect of homogeneous decimation. The right shows you the effect of fractal decimation. And you see it's basically the same effect qualitatively. You lose the extreme events in the dissipation field, and instead of the typical log normal profiles shown by the black lines, you get something that looks increasingly exponential. By the way, also not just the small scale extreme events, but also intermittency in the inertial range as seen through the structure factor is lost. So as you increase decimation, you see that the PDFs of the structure factor become sort of quasi-Gaussian. This, of course, was shown at much larger Reynolds numbers by Lanotte, Luca, and others in their PRL in 2015. But here you see the kurtosis at small scales, which is much larger than 3 for the full Navier-Stokes, starts to approach the Gaussian value of 3 as you decimate. This is for fractal decimation. You see the same thing happens in our simulations with homogeneous decimation. All right, so this is sort of completes the basic tools that we have, the basic setup. And so now the first question we ask is, if we put particles, tracer particles in the flow field given by the decimated Navier-Stokes, which have no extreme events, what happens to the flight crash? So this is the first result you can see here. Once again, the black lines correspond to the full Navier-Stokes, and blue and red correspond to increasing levels of decimation. And I use the same kind of representation as the flight crash paper. And what you see here, interestingly, is that the negative skewness is retained even as I decimate the flow. So even as the particles see fewer and fewer extreme dissipation structures, nevertheless, their tendency to lose energy in crashes is retained. And this is true even if I do it with fractal decimation. So the separation between the dashed negative tail and the solid positive tail is retained. So the decimated flows that I just showed you provide us a clue that extreme dissipation zones are not crucial for flight crashes. So with this in mind, we can return to the full Navier-Stokes and ask what happens there. And one way to kind of look at it in the full Navier-Stokes equations is to condition my power statistics on the local magnitude of dissipation. So essentially, I will look at the power PDF in regions for particles which are visiting mild regions, as well as for particles which are visiting the extreme dissipation zones. So here's the result of the condition statistics. So the blue line is for particles throughout my domain. The red line is for particles only in zones of intense dissipation, here defined as greater than 6 times the mean. And regions which have less than the mean, I characterize as mild zones, and I plot the corresponding power PDF here as well. So interestingly, what you see is that the flight crash signature actually increases in the mild zones. That is, the dashed line is even higher than the solid line for the green curve. But when you look at the red curve corresponding to the intense zones, you see the opposite. You now have a positive skewness of the power PDF. And this we found quite surprising. And one can think of it in the following way, that fluid particles crash not in the intense zones, but rather in the mild ocean of the flow. And instead, in intense zones, they tend to take off, which is sort of the reverse in the sense that they gain energy now more rapidly than they lose it. Okay, so in the last 5 minutes, let me try to put forward the sort of mechanism we thought of to explain these takeoffs. So to motivate our thinking, we looked at the equation for the Lagrangian power evolution, which one obtains by dotting the Navier-Stokes with the velocity. And so you see that the power evolution is governed by the dissipation, work done by pressure gradients, which is the second term. This is work done by viscous stresses. And then you have, of course, the contribution from forcing. Now, Alain Poumire and co-workers in this PRX paper deconstructed this equation and looked at the contributions from each of the terms. And what they show is that the power fluctuations are really governed by the work done by pressure gradients. And so if we focus with that information, if we focus on only the zones of intense dissipation where epsilon is locally large, we can approximate the equation for power with just these two terms. So now with this kind of approximate relation to govern our thinking, it becomes clear that if we have a positively skewed power distribution characteristic of these takeoff events in zones of high epsilon, it must mean that V dot minus grad P is positive and overcomes the negative contribution from dissipation. So that leads us to ask, where would V and minus grad P co-align so that this term is positive? Now, trivially, they're always aligned if you have a Stokes flow where inertia is absent. And so from there, one can think that in a generally turbulent flow, if you look at the viscous dominated regions, which are these kinds of zones of intense dissipation, one may expect the V and minus grad P to align. And so that brings us to our hypothesis that in these zones of intense dissipation, the pressure gradient aligns with the particle velocity and accelerates it and causes it to take off. In the sense, basically gain energy rapidly. So to find evidence for this, this is the plot I showed you earlier. So what I'm going to do now is look at all the particles which are showing you this positive skewness of power. And at those same positions, look at U dot grad P, the work done by pressure gradients. And I'm plotting the corresponding distributions here with the same conditioning. And what you see is that indeed the power is positively skewed, or that, sorry, the work done by pressure gradients is positively skewed in the intense zones. And in the inset, I show you the alignment of the velocity with the pressure gradient. And you see indeed that in the red curve, which shows you the intense zones, you find that the pressure gradient, negative pressure gradient, is indeed strongly aligned with the velocity field. Whereas in the other regions of the flow, it's kind of almost, the positive and negative alignments are somewhat the same. It's almost random. Okay, so with that, I'll try to summarize. So one can summarize all these results by looking at a measure of the flight crash, measure of irreversibility, where we follow the definition in Akshay's work with Rahul Pandit and others. Basically, it's the normalized skewness of the power with a negative sign, so that if you have flight crash, this quantity should be positive. So now if you look at the full Navier-Stokes, which is the three colored dots at 0, this x-axis corresponds to the percentage of decimated modes. So what you see is that, as I just said, in the intense zones, which is the red dot, you have the inverse, which is takeoff events. In the mild regions, you actually have flight crash. And because most of the flow is dominated by mild regions, the net effect is indeed the flight crash signature. And then the decimation results follow on here, which just show you that as you increase decimation, the flight crash persists. Okay, so to conclude, what we see is that Lagrangian irreversibility is tied to the fact that in general, your Eulerian velocity field is irreversible and is dissipating a mean amount of energy, but it's not really tied to the extreme events. And if anything, fluid particles take off in intense zones and tend to crash in the mild vastness of the flow, which leads to the open question of still what is special about the places where the tracers do crash, since they are not crashing in these intense zones. Okay, and with that, the last thing I would like to point out is that we found decimated flows to be quite useful for revealing the kinematic consequences of these intense regions. So if one wants to investigate how important intense structures are for example, collisions of particles, coalescences, breakup of fibers, etc., one could think of looking at the evolution of those objects in a decimated flow. Okay, so with that, I conclude and be happy to take questions. Thank you.
Thank you very much, Jason. In perfect time. So we have a couple of minutes for questions. Let me now check the chat because I discovered there is a chat. Okay, there is one question by Laurent. Decimation not only kills intermittency, but also power spectrum and energy transfers.
Well, actually, the total amount of energy being dissipated, as I said, is the same. So you still have energy cascading through the system. Of course, it has to find a different route than it would have in the normal Navier-Stokes, but you still do have enough modes throughout so that the cascade is retained. This is true, of course, in 3D. If you do it in 1D, then the cascade does stop. But in 3D, the cascade continues. So the flow is irreversible. It does have a cascade, but you don't have these extreme structures.
So it's a way to have a Navier-Stokes evolution without intermittency in some sense. Yes.
Yes.
So
yes,
are there other questions? There is a comment by Beranger. Very nice talk. Indeed, I fully agree. There is Alain. Alain, please go ahead.
Just a short comment. I mean, well, first one would be, of course, with Beranger, etc., saying the talk was very nice. There's this little remark that the first pictures that you showed of this event, which had this sort of strong signature. We looked at a lot of these events when we understood nothing at all, when understanding nothing at all, and we never saw these things sort of developing a very sharp curvature or anything, which all in a sense was some sort of a suggestion that the intense events, as we think of them, if you think of these tiny vortices or these sort of or even these sort of sheets that Takashi was showing yesterday, one thing which was a whoosh jump in a hurry. That doesn't seem to play a role. I mean, which doesn't mean that your analysis was not necessary, of course. But just to say that we never saw. We fully agree qualitatively, but just looking at the trajectories of the things that were of the suspects. That's all.
I see.
But thanks a lot.
Thanks a lot.
I don't know, Jason, if you want to comment back or it's okay. Then are there other questions? If not, I have a very short one. Indeed, another point about intermittency is the dependency on Reynolds number. So it's not only to show that the PDF is skewed and there is an asymmetry, but also whether this asymmetry depends or not on Reynolds number. Did you check by when you show the decimated case if there is a dependency on Reynolds number, as people, as Alain and collaborators have shown in their papers?
Yes, so first I'd like to thank Alain for his comment. So actually in Anand's paper also the normalized skewness, so if you take p cube and divide it by the variance to the 3/2, that's actually independent of Reynolds. So the actual difference between the actual skewness in that sense is Reynolds independent, which is what they showed. So we actually didn't look at the Reynolds dependence. We did the entire thing just for one Reynolds number and different levels of decimation. But what we saw is with the level of decimation, it became independent, the flight crash signature. And that seems to square well with this result that it's also independent of Reynolds, provided, of course, you look at the normalized skewness. Okay. So the tails get fat, but the relative skewness is the same.
Okay, thank you very much. So if there are not other questions, we can thank Jason again. Thank you very much, Jason, and we can move to the third and last talk of this morning section. That is